Hi class, in chapter 11 we will be talking about cleaning agents in part 1, and then in part 2 we're going to talk about personal care and cosmetics. I would like you to understand how soaps and surfactants work to clean, what is the mechanism for that, how a basic soap is made, and recognize some of the basic structures, and then some potential problems with surfactants and the environment. Soaps and surfactants. Let's talk about what surface tension is first, because that's what they affect, and that's why they're called surfactants. Surface tension is the property of the surface of a liquid that allows it to resist an external force due to the cohesive nature of its molecules. It's the force that's driving cohesiveness between the molecules, a property of liquid that causes them to behave as if the surface is covered with a thin membrane. These are definitions, the last two from your book. But surface tension is caused by the molecules being more cohesive, more attracting to themselves than they are to the surface that they're on or whatever they're up against. So water, for example, we talked about how it has hydrogen bonds between the molecules, and if it's not on a surface where it can form, that's polar, where it can form hydrogen bonds and that, then it's going to be very much more attracted to itself, the water molecules to themselves, and it beads up. So you can see it beating up on that leaf there in the picture. And this is a schematic of how that droplet there on the leaf beads up because of the high surface tension of water. And in the picture there with the blue dots, you can see that the water molecules are very much attracted to themselves and not so much to the leaf. It probably has like a oily or waxy surface on it, and that would be nonpolar. So the water is beating up, and then sometimes you see bugs on the surface of water. They can do that, stand on it because of the tight surface tension that water has. We can affect that surface tension of water with something called surfactants. That is short for surface active agents. It's a chemical that it accumulates at a liquid surface and changes the properties of the surface. It changes the surface tension of something like water. And soap is one type of a surfactant. It's the sodium salt of a long-chain carboxylic acid. We're going to see that in a second, some structures of it. And because of the polar and nonpolar parts to the molecule, it goes to the surface of a water droplet or an oil droplet and changes the properties of those. This is a typical soap structure. I said it was a sodium salt of a long chain fatty acid. You should know that. You don't have to draw out structures in this class though. But you can see the hydrophilic end with the sodium positive. It's very polar, and the negative, we call that a carboxylate ion. It's a carbon and two oxygens and a negative charge. And then it has that long hydrophobic chain that comes from the oil. So soaps and detergent molecules can reside at the surface of a liquid and be surface active agents or surfactants. So the nonpolar hydrophobic tails would protrude out of the water surface because that's not what they're attracted to. The nonpolar is not attracted to the water molecules. The polar head part is though, and that would be down in the water. And now the water does not have the same surface that it had before. This is of the nomenclature we're using and the words, how they are subsets of each other. So there are a lot of surface active agents or surfactants. Only some of those are detergents, and we're going to look at a definition of that, and only some of detergents are soaps. So you can see the structure of the soap we just talked about there, and then a detergent may have a different anionic group. Instead of a carboxylate, there is a sulfate there, and surfactants can be other things, and we're going to look at that too. So micelles are an important concept to understand. We talked about these a little bit in the I think it was Water and Other Solutions chapter, where we talked about how we could make oil and water miscible by using emulsifiers, and we talked about how the nonpolar group wants to aggregate together around, for example, an oil droplet, or if you have salad dressing and the oil of the salad dressing, and the polar group wants to be associated with the water, stays associated with the water, and it breaks up the oil into small groups in the water and emulsifies it. And detergents work by the same principle. Detergents in water produce micelles, nonpolar tails aggregating inward and polar out towards the water, and they break up junk on our clothing like dirt and oil. So there you see on number 1 there, the water surface tension would cause it to beat up on a lot of surfaces of fabrics. But if you add a detergent, that lowers the water surface tension, and it'll penetrate the fabric, and it'll also penetrate grease and dirt that's on your fabric, and it just breaks it apart. It pulls it apart. Those polar heads are pulling tiny pieces then of oil into the water, so it can all be rinsed away and go down the drain. Soap is one type of detergent, and it's sodium salt of long chain carboxylic acid, and we make that by saponification. That's the heating of fats or oils in the presence of lye to produce soap and glycerin. So let's look at that in a little bit blown up bigger detail. You recall the chapter where we talked about triglycerides and fats and oils. And that structure is shown on the left, and it's glycerin with still attached to the long chain fatty acids. But sodium hydroxide will come along and break those ester bonds, break those links. With heat, it does it fairly rapidly. I have a video this week that you'll be seeing on my soap making adventure that I had recently. And I chose to use a crock pot and heat so that it would happen more quickly. Also, time will do this. So if you want to wait for weeks, you can also get soap that way. But the end result is glycerol. You see that product, which is glycerin, and that is a moisturizer for your skin, and then the soap molecules. And that's what we just talked about, the sodium salt of the long chain fatty acids. This is my crock pot soap that I made last week. I took olive oil and a little bit of castor oil and coconut oil, mixed it with lye and water, heated it for an hour, and got the soap on the right. I was very happy with it. We've been using it in the shower. There are a number of recipes. I'm not going to dwell on this, and you don't have to know this, but if you're interested, this is the recipe that I used, and it's very important if you do make soap to calculate the lye properly. You have to know for the oils that you put in, how much lye do you need, and these oils all have a different degree of fat in them, like fat bonds, and you have to have the right amount of lye and not too much. You want excess oil and not excess lye, or the soap would be very basic and really irritating. Let's look at a commercial soap like Irish Spring and the ingredients that are on the label. It says soap, and then it says in parenthesis, okay, what's in that? That sodium tallowate would be the sodium salt of tallow, which is beef, I think. I'm not sure it has to be beef, but anyway, it's an animal fat. And then there's a cocoate, which is either coconut or cocoa butter derived from the fat, the sodium salt of that. And then some palm kernel oil they must have used in their formulation, and that's the sodium salt of that. Water, glycerin, which is a byproduct. They say skin conditioner, I guess, for people who may not know, why is there glycerin in here? And it is a skin conditioner, but I guess they didn't take it out. Hydrogenated tallow acid. Now this would be that, and the a couple of the others on here are simply the acidified version of that sodium salt. that's the soap. You want the soap to be on the acidic side and not on the basic side. So they just make sure that some of that sodium taloate, for example, they would acidify it and make sure that there's some acid in there, and you can see that in there. And petrolatum is Vaseline. That coconut acid. Okay, yeah. So the sodium cocoate was from coconut oil, and that's coconut acid. And then fragrance, they have to make it smell like an Irish Spring, and a little bit of salt, and then I think what's a chelating agent to keep it performing better in hard water? Aloe. Now you notice that aloe is way down the list, but that gives them the ability to put aloe on the container. Probably, I think it sounds like a marketing thing. A couple ingredients I would have to look up what they would do, but then we get down to titanium dioxide, which is simply a pigment like you would have in your wall paint, and it makes it white. And then chromium oxide green makes it green so that it feels and smells like an Irish Spring, I guess, or looks and smells. Other surfactants aren't all necessarily anionic. Soap, we said, is based on an anion, the carboxylate anion, and a sodium counterion. And but you can have cationic and non-ionic. So here, for example, a whisk, clean laundry detergent, I assume that's the laundry detergent, has a sulfate in group as an anionic group. And this Lysol has an ammonium, which is a nitrogen positive charge on it, chloride negative charge. That would be a cationic group. And then a neutral group that was in something like Woolite. It's still a polar tail, but it doesn't have a charge, a positive or negative charge. These can perform differently depending on how hard your water is. So what do we mean by hard water? When somebody says, my water's hard, or you have hard water, what does that mean? That means that there are calcium, magnesium, or iron ions in it, and they interact with things like soap and cause a problem. They can cause soap scum and deposits. So what a lot of times we do, and we had this done when we moved in our house. The house was only 4 years old. We moved in a year ago. One of the first things we did was have a water softener put in, because the water is quite hard here. It's coming out of aquifers in the ground, and it must be full of, minerals down there in the rocks. And anyway, the water was hard, and it will ruin things like your dishwasher and stuff like that. And so we got a water softener, and what a water softener does is it exchanges the calcium, magnesium, iron type ions for sodium ions that won't form insoluble salts, which we're going to see what that is in a second. There are synthetic detergents that can remain effective in hard water, but they can cause environmental problems, and some of those have been replaced more recently with more environmentally friendly things. And there are things called builders. I didn't really expect you to know this, but they're compounds that soften water by sequestering mineral ions. They could like chelate around the ion. But here's what goes on to create soap scum in your bathroom, is that soap molecules like you would have in Irish Spring or the soap that I made have the structure there under, like, that shows the sodium salt, the carboxylic acid. And in the presence of calcium, though, calcium interferes with that. It comes in instead of the sodium to the carboxylate, but it's divalent, and so it bridges two soap molecules, and then it precipitates out a solution, because we no longer have this polar head and a nonpolar tail. We have something, if you look down below the sink here, I made this little text, long chain nonpolar group, and then a calcium ion, and then another long chain nonpolar group, and that's what comes out of solution, because it doesn't have the ability to stay in the water anymore like the original structure of the soap. So in water softening, what has to happen is we have to get rid of those calcium ions, magnesium and iron. And this is a schematic of what happens in water softening is that the water that's hard goes into an ion exchange resin. And an ion exchange resin, it's a plastic resin that has ionic groups on it, and they would start out as sodium, but as the calcium and iron, magnesium come in, they latch on to those ionic groups, and the sodium then goes into the water instead of the calcium magnesium, and you have softened water. But after a while, the ion exchange resin gets full of those ions, and it has to be what they call recharged. And you can see how that happens on the right is that the ion exchange resin is just flooded with sodium chloride, a lot of sodium, and so it doesn't exchange back with the calcium, which gets flushed down into wastewater. And that's how, when your ion exchange resin recharges, that's what it's doing, which is why you have to buy bags of salt to put in the reservoir for softening. Detergents need to be decomposable is the important thing about this slide, because if they're not, like phosphates, for example, were causing problems a few decades ago. They cause problems in the environment. Using phosphate in detergents is now banned in many states because they cause something called eutrophication, which is when the water just gets covered with algae, because the algae love the phosphates, and I guess they really act like a fertilizer to the algae, and the marine life goes crazy and messes up ponds and lakes. And so going green is using soaps and detergents, other surfactants that are more environmentally friendly. They need to go into our wastewater and then decompose in a way that doesn't cause problems to the environment. That's just showing you the result of eutrophication and the excess algae in this pond or whatever it is. Some cleaners are green. They claim to be plant-derived surfactants. I could argue that doesn't necessarily mean they're any less toxic, but it didn't take animals to come up with these soaps, cleaning products, which may appeal to you. Your turn. A surfactant is a soap. Think about that. That would be false. A soap is a surfactant, but not all surfactants are soaps. We had that chart of circles that showed what the subsets were, and there's soaps, and then soaps are detergents, and then detergent is a subset of surfactants. What polar group does soap have? And we talked about that a number of times. That would be the carboxylate. It's a carboxylate anion group with a sodium cation. And in part 2, we're going to move on to skin, hair, and oral care, which I think is really another interesting segment. And send me an email if you have any questions about this, and I'll see you in part 2.